I have negative 2 seconds remaining. You know what? Actually, I have my notes. I wanted to mail the next portion to you, and I didn't, because at the very last moment I discovered that I want to change something in the second part, which I want actually to add one more section. And by this reason I will mail today or tomorrow. We will get new parts. But what I want to say that there's always a temptation not to present proofs here. If they are long and written clearly in the notes, then I can always say, you know, read them in the notes, and I will move faster. Still, at least one exception probably should be made. And I do this now. I want to prove the theorem which was formulated last time, called Cartan's theorem, although I think 60% of all theorems which I'm going to give to discuss here belong to Elie Cartan. And this theorem says that if you have a Lie group, G, and a subgroup in the algebraic sense, which in the topological sense is a closed subset, just closed with respect to limits of sequences, then it is a Lie subgroup. So what is missing? What do we need to prove? Is the fact that subgroup of a Lie group is just closed. Actually, topologically, is a submanifold. And the proof is very clear and without unexpected tricks, still has some length. So,
is the converse true?
Converse could be what?
If you have a
Lie subgroup closed, it is by definition. My definition is this. So Lie subgroup by definition is closed.
Okay.
I don't need to prove anything. Always convenient just to give definition, and
sure.
After it, you don't need to prove anything. Maybe what I'm going to say here will be more convenient than my notes, because I will make some pictures which I didn't make in the notes. So we have G. We have H. You remember, G is a Lie group, some dimension. H is a subgroup in the algebraic sense, which is closed as a subset. But I want to prove that H, this is closed, this is Lie group, and I want to prove that H is a submanifold. So what is a submanifold? This means, so this is H, that for every point H in H, there is a chart. A chart is a one-to-one map of some domain in the Euclidean space into G. This is G. And this chart has this property that H is the image of some subspace, or at least of the intersection of the domain of the chart with subspace. This is the definition, and I want to say that it is sufficient to prove it in the case when H actually is E. So it is sufficient to prove the following: that E certainly belongs to H because it's a subgroup. That E has a neighborhood with this property. So this neighborhood, I can say this language has a diffeomorphism onto a domain in the Euclidean space, and the intersection of H with this neighborhood corresponds with respect to this diffeomorphism to a subspace. I do this only for E, because as soon as I do this, I can then apply left translation with respect to an H in the subgroup. And this left translation takes h into h, e into h, small h, neighborhood into neighborhood, and everything is okay. So it's sufficient to construct this neighborhood of E, this property. I want to say immediately that since my what is this? I want to say immediately that that the neighborhood of E, which I'm going to consider, is the neighborhood which belongs to the image of the exponential map. Moreover, this neighborhood is a diffeomorphic image of some. So my neighborhood will be the image of the exponential map of some neighborhood of 0 in the tangent space. So this is all in G, this is all in T, e.g. this is the exponential map. Now, submanifolds. They have tangent vectors, and I begin with the description of tangent vectors. So far, it is not submanifold, but still there will be such a thing as a tangent vector. Namely, let us consider a sequence of points G1, G2, and so on, which converges to E. Certainly, this sequence I can apply the inverse exponential map, call it logarithm if you prefer, and I get a sequence here, also converging to 0 now. Then I suppose the following. I take the straight line here. I take the unit vectors. I say unit vectors, so I assume that there exists, there fixed some Euclidean structure, some metric in this tangent space, not very much not important which one. You understand? And now, let us suppose this sequence of unit vectors has a limit. It will be also a unit vector in TG, right? This unit vector, I call it the virtual unit tangent vector to H. Now, if some V is a virtual unit tangent vector, I can multiply by any real number. I say lambda V, where lambda is a real number, is a virtual vector to H. So there are, I did something wrong. This, certainly, yes. I don't know what to say. This G certainly they should belong to H, otherwise why? So H1, H2. So this vector should belong to H. Then it is called correction. We consider a sequence of points in H which has 0 limit, which has a limit E. And then we apply this construction and we get a virtual tangent vector to H. Now, next remark. Certainly there are such, if E is not an isolated point, there should be such tangent. If E is not an isolated point in H, there should be some tangent vectors, some virtual tangent vectors. Because a sequence, if we take an arbitrary sequence of points, then these vectors are unit vectors. They belong to a sphere. A sphere is compact, and we can always find a convergence subsequence in the sequence. Now, next thing. Maybe this is the main part of construction. Suppose that V is a virtual tangent vector. It is a tangent vector to G, from T to G, right? Let me construct a one-parameter subgroup of G, which corresponds to this vector. You remember that there exists a one-to-one correspondence between tangent vectors and one-parameter subgroups. And I claim that this subgroup, its image, belongs to H. And for this purpose, I will show a picture to you which seems to me more convenient than a couple of sentences, more convincing than a couple of sentences which are in my notes. So, this subgroup belongs to H. I want to prove this. I take an arbitrary point here. It should belong to H, right? It is a local theorem. Everything is within this, within this neighborhood. Certainly, if some portion of this one parameter, excuse me, one should be finished. So let me switch it off. Yes. Now let me consider the construction of a virtual. So this is a virtual tangent vector. I will not draw it because my picture may be overloaded. Every vector. So V is a limit of certain sequence of vectors, and each of these vectors gives you a one-parameter subgroup. This one-parameter subgroup, in the very natural sense, converge to through this one-parameter subgroup. Now, each of them contains an element of H. This is the construction. So we have an element of H here, 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 and all these elements of H, they belong to these one-parameter subgroups, and they have the limit E. A subgroup is H is a subgroup. So if this point belongs to H, then the square of this point also belongs to H. If it belongs to H, then this also belongs to H, right? If it belongs to H, then all this, I just take the parameter value and multiply it by 2, 3, 4, and so on. If this belongs to H, then all this belongs to H. Now this picture, as it seems to me, shows clearly that there exists a sequence of points in H which has this limit. Because this distance is smaller and smaller, because this sequence of points of H, converges to E. So in the next one, they will be very close to each other. And certainly, every time, this corresponds to some value of parameter. And we take, in these one-parameter subgroups, elements which are closest from this sequence, closest in terms of the parameter to the value of parameter here. This shows that actually every point in gamma V is a limit of certain points of H. And this is where we use the closeness of H, we see that this point belongs to H, and hence the whole one-parameter subgroups, however, at least within this neighborhood, but actually if a portion of one-parameter group belongs to it, then the whole one-parameter group must belong to it because one parameter group is a subgroup, and which is generated by any small interval. Good. So we have at least some amount of one-parameter subgroups in H. Good beginning. Now one more remark. Suppose that we have in H a curve, a smooth curve through E, and suppose that this curve gamma belongs to H. I want to say that in this case, the velocity vector at E is a virtual tangent vector to H, simply because a virtual to H, simply because we can now take a sequence of points in this curve which converges to E, and it's very clear that the vectors which I defined before will converge to this V after normalization. Okay? It's almost all. Now next thing, and I think two steps remain. Yes, two steps. Both are very simple. First, we have some subset of the tangent space TEG, right? Virtual tangent vectors. Nothing can be less useful than a subset, if it is not a subspace. It is a subspace. So my next claim that the virtual tangent vectors to H form a subspace of TEG. Why so? Well, subspace should be closed with respect to multiplication by numbers and by the addition. Everything is okay with multiplication by numbers, by definition. Addition. Suppose that we have two virtual tangent vectors to H. Then we consider curves in H, for example, one-parameter subgroups. So this is, say, gamma 1 of t. This is gamma 2 of t. Curves with these velocity vectors, which belong to H. And for example, one-parameter subgroups, and we already know that they do belong to H. Now we take products. Gamma 1 of t times gamma 2 of t for every t. It is not a one-parameter subgroup in general, but I don't need this. What I need is that this product gamma 1 of t times gamma 2 of t belongs to H, because gamma 1 of t and gamma 2 of t separately belong to H, and H subgroup, right? So this curve totally lies in H, and hence its velocity vector, which is the sum of the two vectors. This is c, this is eta, this is c plus eta. We also know this, that the multiplication in the group corresponds to the addition in the tangent space with respect to the exponential map. So yes, the sum of two virtual tangent vectors is also a virtual tangent vector, and hence there exists a subspace. A subspace W in T G subspace, which precisely is the set of all virtual tangent vectors. Now I can take in, so W is in T E G. I take the exponential image in G, and what we already have, that yes, it consists of one parameter subgroup. So yes, it is it is a submanifold of G, and it's a part of H. The remaining thing, this word part, not a part, is the whole H. So my next and last claim, that actually, if your neighborhood of E is small enough, then this neighborhood consists no other points of H, no points of H which do not, I prefer to erase this because I need to extend my picture. So my claim is that it is locally some neighborhood of E. H does not have any other points, and this will be all, right? Consider in TE G complementary subspace. For example, orthogonal complement. We already used an Euclidean structure. This is exp of Z. Now I say that a neighborhood, some neighborhood of E, actually can be identified with a neighborhood of 0. So exp, we have this map into G, simply the multiplication cross here. Multiplication, we take an element here, an element here, and take their product. And this map, at least at E, its differential is an isomorphism. And hence it is a diffeomorphism in some neighborhood of the point E, and we do not consider anything outside of this. So, what do I want to prove? I want to prove that in some neighborhood of E, H has only this set. Suppose it's not so. What does it mean? This means that there is a sequence of points in H, yes, which converges to E, and says that no one of these points, the whole sequence, lies outside the exponential image of W. If so, this means that no neighborhood of E actually is free of points of H, not in exponential image of W, right? Now, sufficiently close to this point, every point in this sequence, every point at all, actually is the product of a point in exponential image of W, a point in exponential image of Z, right? So we can project this sequence onto the exponential image of Z. This projection actually takes points in H into points in H because this projection is a multiplication or division by elements of exponential image of W, that is of H. So the sequence also belongs to H. This sequence, as any other sequence, determines a certain virtual tangent vector to H, right? Namely, we take unit vectors. Certainly, I maybe had better to draw them there. Unit vectors. And they have a limit, at least some sequence of the sequence has a limit, because they belong to a sphere, which is compact. So, we take some subsequence of the sequence, and we get a virtual tangent vector. Where? In Z. Right? And this is a contradiction. Because W is the set of all virtual tangent vector, so no non-zero, it's a unit vector. No non-zero vector, no non-zero virtual tangent vector to H can belong to Z. This contradiction, which completes the proof of theorem. So step by step. First, we take H. My first remark was that it's sufficient to prove this is a manifold in a neighborhood in proximity of E. And everything works. Second, I defined something which should be a substitute for a tangent. I call it virtual tangent. Virtual is temporarily then we find this is maybe of all my constructions, this is the most sophisticated. We find that if we have a virtual tangent vector to H, then the whole one parameter subgroup is determined by this belongs to H contains a whole curve. Very obvious that the set of virtual subspace closed with respect to addition. So we have some subspace W in TG. We have its exponential image, which is contained, is submanifold of G is contained in H, yes, and then we simply find that H cannot contain sufficiently close to E. Because then we have a whole sequence converges to E and do not and belongs to the exponential image of W. And as soon as we have this, we can easily construct an impossible virtual tangent vector to H, which is contained in Z rather than in W. My notes contain. There are some pictures which are not there. Otherwise, it is all written in my notes, so you can read this. And this is all I could say before I admit that TG is not just a vector space. So we sort of now begin studying other things and questions regarding the part which is over now. So very much topological part. Even TG, tangent space to G, is the usual tangent space to a manifold. But now I want to say that TEG has an additional structure, an additional algebraic structure, which makes this a Lie algebra. I first define the structure, then we will discuss what Lie algebra is. So, TEG is a vector space. It has usual vector space operation, addition and multiplication by numbers, and also it has a binary operation, bilinear binary operation, which is called the commutator. There are several ways how to define it, but one of these ways is very clear. We do the following. We take two vectors, Xi and eta in T, G. Then we form left invariant vector fields, or right invariant vector fields. The result will be the same. You remember how it is done. I take Xi and I just expand it to a vector field by applying all possible left translations. The same with that. These are two vector fields. And vector fields do have commutators. Also a vector field. And also left invariant, this is obvious. If we apply left translation, then LC is mapped onto LC, L eta onto L eta, and commutator onto commutator. And every left invariant vector field is actually L something. And the something by definition is Xi by notation. Is Xi comma eta, and by the terminology it is the commutator of Xi and eta. This is a very clear definition. The properties are also very clear. This operation, this binary operation, is bilinear. I even will not write anything regarding this. Then it is anti-commutative, and then it is not associative in general. But this describes the celebrated Jacobi identity. The fact that this relations hold for our new operation in TEG follows from the they also hold for vector fields in general. And for vector fields, there are several different definitions of the commutator. And maybe for different definitions, the level of difficulty of this fact may be different. But the most clear definition, a vector field is a derivation in the ring of functions, algebra of functions on a manifold. Derivations have compositions which are not derivations in general, and have commutators which are derivations. And definitely the commutators satisfy this. Properties follows immediately from its description. So we have a Lie algebra structure in TEG. And at this moment, we need to somehow to reflect it in notations. The notation TEG is never used. So we have a Lie algebra. As a vector space, it is TEG. And one way to denote it is this, LeoG. So this is TEG with this additional structure, with this commutator structure. Or there exists another way, maybe less formal, but very common. If a Lie group is denoted by some Roman letter, capital Roman letter, then the corresponding Lie algebra is denoted by the same letter in the lowercase letter in the German alphabet. It's called Gothic fractor. I don't know how you call it. It is not too common now even in Germany, but in mathematics it is quite common. Mathematicians have so many notations usually that they need several alphabets. And so in these cases it is G, this is H, S. S actually has two different ways to, so I denote it like this. So the corresponding Lie algebra is denoted by the same letters, but in a different alphabet. It is very common. Now, one more description of the commutator, which actually comes from another description of the commutator vector fields. If you have two vector fields, say on this blackboard, how to define their commutator? Two vector fields, x and y. I prefer not to draw them because it will be a mess. Then we take a point and take a trajectory of the vector field x up to the value of parameter t. T is some positive number. Then we stop here and consider, starting at this point, a trajectory of the vector field y, again up to the parameter value t. Then we do the same with negative x, and the same with negative y. In general, we do not return to the initial point. And this point I denote as zeta actually t squared. It is closer to the origin, the distance from this point to the origin actually has the order of t squared rather than t. Still, if I do this for every t, at least for positive values of at least for the positive values of the parameter, I have a curve which has a velocity vector, and this vector belongs to the vector field xy. So we do this for every t. We get for every positive value of parameter, we have a point, we have a curve, and we have a velocity vector. This is the usual construction which is normally used in analysis, if you don't want to be too algebraic. Now, we can do all this actually for the Lie group and Lie algebra. Because I say trajectory, but we know that this trajectory is called also one parameter subgroup. So we have we have G. We have this space which is called G now. And then we have two vectors, xi and eta in G. Now we take this is E. I want to define one vector. This is E. This is gamma xi of t. Let me write the square root of t. Now, I take the one parameter subgroup corresponding to it, and I shift to this by left translation. So this, I apply this, apply this, apply this. What I get is the following in the group. I get gamma xi of square root of t times gamma eta square root of t times gamma xi, negative xi, or if you wish, gamma inverse square root of t, and xi, and gamma inverse eta square root of t. I denote this as gamma of t, and the velocity vector of this is precisely gamma dot of t, is precisely gamma, well, is precisely xi at m velocity vector is 0. This is the same construction, but sort of presented in a more traditional way. Is it okay? If so, I have this description of the commutator in the Lie algebra, Lie G, but this This use may be very much inconvenient in many respects, but it's very much convenient in one respect. Because if we have a homomorphism between two Lie groups, Lie homomorphism, smooth map, which is also a homomorphism in algebraic sense, then its differential at E is a map of TG and TH, denoted now as G and H in German alphabet. And I claim that actually this is a Lie algebra homomorphism, which means that it takes commutators into commutators. It can be easily proved if you use my initial definition, but it becomes absolutely obvious if I use my second definition. Because certainly a homomorphism takes one parameter subgroups and one parameter subgroups, respects multiplication, respects everything. So it is very clear this is so. Now I still have 9 minutes. I want to say some important things. And if I have more time, I will say also some less important things, also important. Well, not everybody will agree with me. But I can say that technically, the main thing in the Lie theory is this transition from a Lie group, from a Lie homomorphism between Lie groups, and homomorphisms, Lie algebra homomorphism between their Lie algebras. Because this correspondence between purely topological between set purely topological objects and something very much algebraic is more or less one-to-one. The following holds. First, if we have to by the way, for my purposes now, I prefer to have connected groups. At least G should be connected. Otherwise, I don't know what happens in the other components. So G is connected. Better everything is connected. But G definitely is, because if G is connected, then the image belongs to the component of H. So we can easily assume that both are connected, G and H. If two Lie homomorphisms, G into H, have the same differential, then they coincide. So this small thing, differential at one point, just imagine 4 functions. Almost nothing. So we have two. For this purpose, we even don't need Lie algebra structure. If we have two different homomorphisms between Lie groups, which happen to have the same differential between the corresponding Lie algebras, then they are the same themselves. And actually, you can probably immediately say how to prove it, because it's very easy. Let's begin. We have these two homomorphisms between G and H. They may be very different. Now, we can apply this to a one-parameter subgroup of G. The image will be a one-parameter subgroup of H, right? For both homomorphisms, but the same one-parameter subgroup, because one-parameter subgroups totally are totally determined by the velocity vector 0, right? Velocity vector at E. So at least such two homomorphisms F and G must coincide on every one-parameter subgroup. This gives you more or less all. You can say something wrong, but it's convenient. Actually, the group is totally covered by one-parameter subgroup. So if two homomorphisms coincide on a one-parameter subgroup, they coincide everywhere. If you happen to know that this is not wrong, there are counterexamples. Then you can say differently. It is very easy. I have no time to do it now. Very easy to understand that actually every Lie group, connected Lie group, is generated by any neighborhood of the unity. That is, every element which you can imagine of G can be presented as a product of elements belonging to a chosen neighborhood of E. And this is more or less obvious. There is an exercise in my set of exercises, but I can prove it next time. This certainly implies that if two homomorphisms coincide on a neighborhood of E, they coincide totally, which happens. This theorem is relatively easy. There exists another theorem, opposite direction. Suppose that we have two Lie groups, G and H, and no Lie homomorphism. But we have a homomorphism between their Lie algebras. Of Lie algebra of G into Lie algebra of H. Say both. Do you think that this arbitrary map between Lie algebras is the differential of a certain map, certain Lie homomorphism? Does it seem? Maybe not quite.
Are we simply connected? Are we simply connected?
Yes, Colin. I didn't expect to have the right answer immediately. Actually, if G is simply connected, then yes. Otherwise, it is possible that your homomorphism between Lie algebras is the differential of Lie homomorphism of some covering over G into H. Or, if you prefer this language, of some multivalued homomorphism of G into H. Then it will be okay. But certainly it is so. Just imagine that G is a circle, and H I don't know what. Then the Lie algebra of G is just one-dimensional space, just one tangent vector, right? The image of your of this vector is some vector arbitrary, a vector in the Lie algebra of H, right? So this circle should be mapped onto a one-parameter subgroup, which corresponds to this arbitrary vector of H. But if you have a really arbitrary vector of H, then the one-parameter subgroup will not be a circle. It will be a whole line, right? A line is a covering over a circle, so everything is okay. So this theorem, this is the statement of the theorem, that we do have a one-to-one correspondence between Lie homomorphisms and Lie algebra homomorphisms. If we additionally assume, for example, that G is simply connected, not just connected, and this will work perfectly well. Or in another way, actually, Lie theory, as was created by Lie, is not a theory of Lie groups. There exists a notion which I'm trying to avoid here, of a local Lie group. So actually, we have a domain in Euclidean space and multiplication which is defined in some neighborhood of 0. Local Lie group, it's very easy to define. Local Lie groups also have Lie algebras. Absolutely the same. We don't need any global object to define a Lie algebra. And then certainly it is true. Actually, you can even not, without speaking of local Lie groups, you can speak of local homomorphisms. A local homomorphism is something which is defined only in the neighborhood of E, and satisfies the homomorphism conditions as much as it can satisfy them. When the product is defined within this neighborhood, then yes, it is taken to the product. So this is how it works. The true correspondence is between Lie homomorphisms, between Lie algebra homomorphisms and local Lie homomorphisms. And then we need to speak of coverings of something if we want to globalize it. And then my last word. Yes, I have several seconds for this last word. My last word. Representation. What is a representation of a Lie group? You can think this or that, but actually it is a homomorphism, Lie homomorphism, of the given Lie group into the group of matrices, GL and something, right? R or C, depending on your field. A representation of a Lie group gives rise to a representation of a Lie algebra, which is much easier to study. And more or less, up to this covering, more or less, these two theories are absolutely equivalent. Not only these theories, actually it is the first step to the full picture that the whole theory of Lie groups can be presented as an algebraic theory of Lie algebras. You just need how to translate one statement into other. This is what I am going to do. Now I have to stop actually